Turning to slide 13, here are some key findings from the Sparrow-Mutian paper regarding what we call a reciprocal cross-lag panel model with or without random intercept. The model is identified for t equal to or greater than 3 time points with equality of the reciprocal effects across some of the time points at least. And the model has t minus 1 more parameters than the regular CLPM or RI-CLPM models. It's equivalent to those models if you add t minus 1 restrictions. So for instance, for t equals 3, then t minus 1 is 2. So we apply 2 restrictions, and we can for instance assume that, or we can only assume that the reciprocal effects are invariant for time 2 and time 3. With 5 time points, we have t minus 1 equals 4 restrictions, and the reciprocal effects are invariant then, for instance, for time 2 equal to time 3, and for time 4 equal to time 5, or other combinations that you may want to explore. The models are then identified with those 4 restrictions. The results will be slightly different, and you can do an analysis where you test the sensitivity of that choice. For t equals 4, that is for even number of time points, you don't have a natural choice. Could, for instance, use equality for time point 2 and 3 and let 4 be different. As long as you have 3 restrictions, the model is identified. When I do the analysis on real data, I usually have full time invariance for the reciprocals, which I find to be reasonable. And then you would have a model that uses fewer parameters than the conventional ones. One important note here on slide 13 at the bottom is that the cross-lag effects of this reciprocal cross-lag model are different from those of CLPM or RI-CLPM. So the cross-lag effects, those effects that they have in common, they are not going to get the same estimates. And that has implications then, of course, for interpretation. Going to slide 14, we get a little bit more technical. And a important finding here is the model has 2 solutions. It's a little bit like when you do quadratic equations, where you have a quadratic equation with a plus or a minus solution, and you choose one solution as admissible and the other can be discarded. One needs to impose restriction to choose this acceptable solution, and that's essential for bootstrapping and Monte Carlo simulations, where you have different draws or different replications, and in one draw or one replication you get one of the 2 solutions and the other solution. So then you're mixing apples and oranges, so you need a restriction. Now one can think of the 2 solution issues, this duality issue, as an innocuous, harmless type of non-identification, pretty much in line with one-factor analysis, where the factor loadings can be either all positive or all negative and give the same fit. Just changes the interpretation of the factor increasing or decreasing. So you don't have infinitely many solutions as in typical non-identification, but you have distinct sets. In this case, for the reciprocal model, you have 2 sets. Now, another consideration is that R squared for some of the within equations may be negative when the restriction is not fulfilled or applied. Another point here is that the distribution of the reciprocal estimates is non-normal, and non-symmetric confidence intervals may therefore be needed, using either bootstrapping or Bayes, although Bayes is not available for this reciprocal model yet in M+. Now, the non-normality may not be that pronounced in many situations, and you may choose to ignore it, but it's probably a safe thing to do to get a conservative confidence interval. We also find in this paper that there is a need for larger sample sizes than for CLPM and RI-CLPM to get sufficient power to detect the reciprocal effects. The estimates may be okay at the same sample sizes as the classic models, but the power for the reciprocal effects needs a certain number of time points and sample sizes. And we'll see that in the Monte Carlo study that I'm going to show you in a while. Now, when cross-line effects are not included in that model, the reciprocal only model that I called it, there are not two solutions. You don't have this problem. But R squares can still be negative if you don't apply a restriction. However, non-symmetric confidence intervals are not typically needed for the reciprocals. On slide 15, then, I'm more explicit about the kinds of restrictions that I mentioned in our paper. Two kinds, I refer to them as restriction A and restriction B. And the reciprocal effects here, I call them R, Y, and RZ for two variables, Y and Z. And one restriction is that the product lies between 0 and 1. And the restrictions are therefore such that they are either positive, both of them either positive or negative. So 2 positive gives a value that's positive, 2 negatives gives a value that's positive. This avoids dual solutions, the two-solution problem, and avoids negative R square, and is suitable for real data analysis. Restriction B is formulated a little bit differently. It avoids dual solutions only. You can still get negative R square. And it's useful for bootstrap distribution, studying bootstrap distributions before applying restriction A. It's also suitable for Monte Carlo studies because restriction A always gives power equals 1 for the reciprocal effects, irrespective of sample size. So that's not useful. I won't go into why that is so here. Now, guidelines for real data analysis are given here on slide 16. Step 1, estimate the model with the non-duality of the R square constraint A, and also use the starts option in the analysis command, like starts equal 20 or 50 or even 100 in some cases, to ensure getting the best solution. It's still a fast analysis. If both reciprocal effects are significant, use that model. Very often, though, one of the two reciprocals are not significant, and you can eliminate that parameter and re-estimate the model. And also a little technical, step 4 here, if one of the reciprocals has a 0 estimate, the solution is at the border of the constraint, then the product is 0. You can re-estimate the model with the non-duality constraint B only to check if a solution is found with different reciprocal signs and better fit. More on that in the paper. So those are some of the more technical aspects of the analysis discussed in this paper, the technical part.